You'll catch that later. All right. I'm glad you said something though, because I definitely was not, and I would have been totally distraught. All right. So the plus charge has to go here. Does everybody agree that this site right here is the allylic site?
Yes.
Can you zoom out a little bit? Thank you.
Yep. So that is my allylic site. Is that right?
Yes.
So what happens next what's the next step? The next step is to add bromine in. Sorry. It's for bromine to attack. Now on Monday we talked about the fact that you get two different products, right? One where bromine attacks directly, and then one where bromine attacks at the resonance site. If I drew the resonance form for that. So let's do the direct attack first. What would that look like?
It'll go where the plus line is.
It'll go right here, right here. Is that right?
Mm-hmm.
So that product is going to look like this, right? Where bromine is here. This alkene didn't get touched, and then the methyl group is still there. So that's what we call 1-2 attack or direct attack. Is that right?
Yep.
All right. So what about the resonance? What about the 1-4 attack? What would that look like?
It'd attack at the alkene. And
So
then,
let's draw the resonance form. Yeah, it would. You're right. It would attack there, but let's just draw the resonance form. So the resonance form for that allylic carbocation would look like this. But the plus charge will be there now. Is that right?
yeah.
Because I'm going to take the pair of electrons and move them here.
So do you have to draw the resonance form first, or can you just take the bromine?
I'm doing that for clarity, but if you're able to show the attack like this, right? Because that's always going to happen. The bromine is going to attack, and the double bond is going to shift over. But since I've been teaching this, like a lot of times, showing the resonance form helps people to understand it a little bit better. So, but you don't have to show that. Yep. Right. So that product is going to that intermediate will eventually lead to this product. Is that right? Because the bromine is just going to come in and attack that plus charge. Yay, nay?
Yeah.
Questions?
Okay, I have a quick question. Oh, Kayla, go ahead.
Oh, you can go ahead. I was already talking earlier.
Okay. This is the same problem we did on Monday, correct? Because
yeah, but we're looking at a different alkene. We're looking at this alkene because they both can attack.
okay, because I think my products look different on my paper, and I'm a little confused.
I think he's attacking from a different double bond. So before we attacked from one double bond, this is a different one.
Yeah, on Monday we did this double bond right here.
Okay.
Right. So yeah, you're going to get different. So you should get 4 different products. Say that again.
I said I have a question about the product. So you get the same products but it's just at different temperatures.
Yeah. So when you do a reaction like this, if you do it at low temperature, right, you're going to get both products, but the major product is going to be the product that you get from direct attack.
Okay.
Right. And then if you increase the temperature like we did down here, that product the major product is going to be the one that comes from the resonance attack.
Right. Okay.
Because
Because I was looking, I was like, they all have the same product, but I'm trying to figure out why.
Say that again now.
I said because I was looking at them and they all like have the same products.
You mean like the bromine adding in?
Yeah.
Yeah, because you add in HBr, so they're all going to add H and Br across the double bond. But the difference is the intermediate is always going to be a Lily, and then that intermediate can get attacked two different ways.
Okay.
Right, and so you end up if you use the alkene that's highlighted in green, right? That's going to give you one intermediate that can get attacked two ways and give you two products. If you use the alkene that's highlighted in pink, that's going to give you an intermediate that can be attacked two ways and give you two different products.
Okay. Cool.
Yeah. Any other questions about that?
So for dyeing, like, will they always produce 4 different products, or not always, but most of the time?
Yeah, most of the time, yes. It just depends on the type of dyeing you're working with. Any type of dyeing like that's conjugated like the one we have here, yes, you're gonna get 4 different products.
Okay.
But sometimes your alkene can be conjugated. I think there's a problem in here that we're gonna do where your alkene is actually conjugated with a benzene ring, and the benzene ring doesn't react. So really, you only get 2 products in that.
Okay.
Yeah. So I think there's a problem that we're gonna do today that kind of illustrates that. All right. So let's go to the next question here. Let me erase all this stuff. I can't even get mad at the person who left it on the board. It was me. That's a big problem at Skiggy. People don't respect when other people coming in to teach. I had to slap 2 people before.
Slap?
I ain't calling no names though, because I don't want y'all putting that on Snapchat or Instagram.
Dr. Russell, you just killed me with that one. You said you had to slap him. I am dead.
2 people. 2 people.
You sound like me. You are funny.
I had to give him that Rick James treatment. What did the 5 fingers say to the face? Anyway, so let's look at this problem right here. This problem is dealing with the kind of the how do I want to put this? It's dealing with the equilibrium or lack of equilibrium depending on the conditions. So one of the things that was talked about in the video is that if you do the reaction at 0 or at low temperature, you don't set up an equilibrium, right? It's an irreversible reaction. Right? It's irreversible. So anytime you do the reaction at low temperature, it cannot go back, right? Once you get to the intermediate and then you cross over the barrier to get to the product, it can't go back. It's irreversible. When you do the product at higher temperature, so like at 40 or 37 or room temperature, then that is a reversible reaction. All right. So low temperature, irreversible. High temperature is reversible. It just a higher temperature is reversible. Right. So I don't know if you saw like the video, so I'm just going to give you a quick illustration of what that means. Right. So this is my intermediate. Right. And then I can go at low temperature. I'm going to go here. And then at a higher temperature. That's a bad color. I'll go here. Right. So this is product. This will be product 2, and then the top one will be product 1. Which product is more stable? If you're looking at keep in mind, let me do this too to make it plain. All right, this is an energy diagram That's energy on the y-axis and time on the x-axis. Of those two products, and energy is increasing in that direction. Of those two products, which product is the most stable?
Product 2.
Number one.
Okay, energy is going up this way now. Come on, finger, do what you're supposed to do. So energy is increasing. So if product 1 is above product 2, that means it's higher in energy. Are you following that?
Mm-hmm.
The product one not above product 2.
Huh?
You said product 1 is above product 2 is in higher energy.
Yeah, it's higher in energy. If energy is increasing going from bottom to top like that, if we start at 0, let's just give some arbitrary numbers. Let's say at where product 2 is, that's 1 kilojoule per mole. And then where product 1 is, let's say that that's 3 kilojoules per mole. Are you following? You're going up as you go from bottom to top, the energy increases. So this one is going to be, this is arbitrary now. It's not, that's 3 kilojoules per mole, and then product 2 will be 1 kilojoule per mole. Yes or no?
Mm-hmm.
Yeah.
All right. So if product 1 is higher in energy, is it more stable or is it less stable than product 2?
It'll make it less stable.
Less stable. Anytime something is higher in energy, that means it's less stable. Let's write that in there. Right. So product 1 is a less stable product. Product 2 is, oh, that's a change colors. So product 2 is going to be more stable. Are you following? Don't jump off the boat yet. All right.
Yeah.
Go ahead. Did you have a question?
Oh no.
Okay. So now let's go to the other side. So that's the thermodynamic part. Let's look at the kinetic part. Which of the two curves, if we start on this side right here, which one do you think is happening faster?
Product 1.
Product 1?
Yes.
Yes, the purple curve, right? How do you know that? What do we look at to determine that?
The activation energy.
Activation energy. Very good. So I'm gonna erase all this, as much of this stuff as I can. All right. So for the first product, this is the activation energy, right? All right. It'd be delta G double dash. Is that right? And then for the second product, this is the activation energy. That's P2. Yes or no?
Mm-hmm.
So product 1 is going faster, but product 2 is more stable. That's the difference in the what we call the thermodynamic and the kinetic product. The thermodynamic product is the more stable product. The kinetic product is the fastest form product. Right, so the kinetic product is formed fastest. Thermodynamic product is most stable. The problem down here is talking about reversibility, right? That's what we're trying to get at. I'm trying to get to that. All right, so you take both of the products done as zero, which would be what? Kinetic or thermodynamic at low temperature?